Hello, and welcome to the last section of Chapter 4. Today we're going to look at applications and models of trigonometry. And we're going to start out with an example. Example 1 says to solve the right triangle shown in the figure, where A equals 20 degrees and B equals 15. So right here's my triangle that I'm going to solve. Typically, if a triangle is not given to you, I would highly suggest that you make at least a sketch. And if you recall from geometry, the side length that is opposite of the angle is going to be the lowercase letter. So this here would be like lowercase a, this here is side length lowercase c. So as you can see, we have angle B that we have to solve for. We have side length A and side length C. So the first thing I'm going to do is I'm going to start out by solving for angle B. And I'm going to show that like this. And angle B is going to be found by taking 180 degrees and subtracting 20 from it and our 90-degree right angle. So this is going to give me 70 degrees. And typically when I'm solving a right triangle, there's multiple of ways that you can do things. However, I like to use this side length and angles that are given if at all possible. So I see that if I use my side length of 15 and my angle of 20, I can actually go ahead and find my side length of A here. And A is going to be related to my angle. A is opposite of, and I'm given an adjacent angle here. So here's my adjacent side, here's my opposite side. So because I have an opposite and adjacent, that is our tangent. So we can say the tangent of 20 degrees is equal to our opposite side length, which is A, divided by our adjacent, which is 15. So now, if I go to get A by itself, I'm going to multiply both sides by 15, and I end up with A is equal to 15 times the tangent of 20 degrees. You do need to have your calculator in radian mode. And when you do this, you'll see that A is approximately equal to 5.46. And you could take a similar approach to finding side length C, or because you know what A is and you know what side length B is, then we can find C by using the Pythagorean Theorem. So I can say C is going to equal the square root of 15 squared plus 5.46 squared. And if you add those two squares together and then square root that answer, you'll see that C is approximately equal to 15.95. And if we do a quick little double check, we know that the hypotenuse is our longest side, so that side length should be a little bit longer than either one of these. And 15.95 is slightly bigger than 15.9 or 15 even. So by solving, I was able to identify my angle B and my side length C as well as side length A. Next is example 2, which says a ladder 16 feet long leans against the side of a house. So the first thing I want to do is I'm going to sketch this. I have the side of this house here, and we can just draw a roof if we want. And we have a ladder that leans against the side of the house. So it's going to look something like that. I know that the ladder is 16 feet long. We want to find the height h right here from the top of the ladder to the ground if the angle of elevation is 74 degrees. Now remember, an angle of elevation is the angle off from the horizontal. So that tells me I have a right angle here, and that this angle here is really equal to 74 degrees. And by the angle, I mean this little bit right in here. So again, I'm going to use the side lengths and their relationship to the angle. So I am given a opposite side length and a hypotenuse. So an opposite and a hypotenuse is related to my angle with a sine value. So I can say that the sine of 74 degrees is equal to my opposite side length, which is h, divided by my hypotenuse, which is 16. And from there I'm able to solve for h by multiplying both sides by 16. So h is equal to 16 times the sine of 74 degrees, which in this case is equal to approximately 15.4 feet. Next is example 3. And example 3 says, from a point 65 feet in front of a church, the angles of elevation to the base of the steeple and the top of the steeple are 35 degrees and 43 degrees. We want to find the height of the steeple. So again, I'm going to start out with a little picture. I have this little church that looks something like this, and it has a steeple. And if you want, you can draw a door and some windows. Okay, but anyways, I have a distance from the church that is 65 feet. I know that the angle of elevation from the base of the steeple, so from here to that distance of 65, this is going to give me 35 degrees. And I'm told that the angle of elevation from the top of the steeple to that same point, 65 feet away, so this angle here now is 43 degrees. Now I want to find the height, or from here to here, I want to find that distance of the steeple. So I'm going to start out by dealing with the smaller triangle first. So in order to find the height of the steeple, I'm actually going to have to find the whole height from top to bottom, because essentially if we just draw the triangles here, we really have something that looks like this, where everything's coming together at the same point. So because I'm given this angle here first, and I know that this whole distance is 65 feet, I'm going to look for this height, so I'm going to call this h sub 1. And h sub 1 then is related to my angle because it's opposite, and I'm given an adjacent side length of 65 degrees. So opposite and adjacent from my angle is a tangent. So the tangent of 35 degrees is equal to the opposite, which is h sub 1, divided by the adjacent side, which is 65. So if I go to solve for my height 1, I end up with h sub 1 is equal to 65 times the tangent of 35, which is approximately equal to 45.513 feet. And then I'm going to have to do the same thing, except this time I'm going to be looking at that overall height, and I'll call this h sub 2. So h sub 2, now my ratios of my sides and lengths haven't really changed, so h sub 2 is going to be found by taking the tangent of 43 degrees this time, because this is a larger angle, and multiplying that by 65. So when I solve for h sub 2, I get 60.613. So now I have the big height and I have the little height. I want to know the distance in between those two, or this height right here. So to find my, I'm going to call this h sub s for height of the steeple. This is going to be equal to 60.613 minus 45.513 feet, or a total height of 15.1 feet. And the last thing we're going to look at today deals with bearings. Now, when we're talking about surveying or navigation, the directions in surveying and navigation are typically given in terms of what we call bearings. And a bearing measures the acute angle that either a path or a line of sight makes with some fixed north-south line. So what we're looking at typically is if this is my north-south line, north being up here, south here. Okay, if I have an angle measure, and let's say the angle is over here, we're actually going to measure it off from the north line. Likewise, if I have an angle that falls down in this quadrant, I'm going to measure it off from the north-south line right here. And typically they're shown like this angle right here that we just did would be shown something like S 35 degrees and then E. And how this is read is we are 35 degrees east of south. And one thing from the story problems that you're going to have to do that I want you to keep in mind, when you are talking about air navigation, these bearings are measured in degrees clockwise from the north. So just kind of keep that in mind. You're not going to have a south bearing. It's actually going to be measured off from the north line. So our last example for today says, a sailboat leaves a pier and heads due west, which means straight west, 8 knots. After 15 minutes, the sailboat tacks, changing course to 16 degrees west of north at 10 knots. We want to find the sailboat's bearing and distance from the pier after 12 minutes on the course. So, the first thing we're going to do is we're going to sketch this all out. Okay, it says that a sailboat leaves the pier and heads due west. So if my sailboat starts out right here, let's just call this point A for a beginning, and heads due west, it means it's going to head straight west at 8 knots. So, and I realize that this probably isn't common knowledge, but 1 knot is equal to 1 nautical mile. So in order to find out the distance that was traveled right here, it says it's heading due west at 8 knots. We need to take the distance that's being traveled and multiply it by the time to get the total distance. So think of knots as like a miles per hour almost, okay? So if I'm going 8 miles per hour, to find the total distance, you have to multiply it by a unit of time. Same thing with a knot. If I'm traveling 8 knots due west, I need to multiply it by a unit of time to get the total distance. Well, in this case, it says after 15 minutes, the sailboat tacks and changes course. So for 15 minutes, we are going 8 nautical miles, and 15 minutes is a quarter of an hour. So I'm going to take that 8, and I want to put NM for nautical miles, and I'm going to multiply that by 0.25 hours, and 8 times 0.25 is actually equal to 2 nautical miles. So that's my total distance here. So then to continue on with my drawing, it says that our course is going to change from going due west to going 16 degrees west of north at 10 knots. So 16 degrees, what I'm going to do is I'm going to kind of come in here and I'm going to draw in this dashed line to represent my north-south line. And I'm going to be 16 degrees west of north. So that tells me I'm going to have to be 16 degrees on the left-hand side of that north-south line. So I'm going to come over here. This here is 16 degrees west of north. And now we're going to be traveling for 10 nautical miles, or 10 knots. And we have to find out how long we're going. And it says the sailboat measures the distance from the pier after 12 minutes. So 12 minutes out of 60 minutes is going to be 1/5, or 0.2 hours. So when we multiply 10 by 0.2, we get 2 nautical miles. So it wants, the actual question that was being asked is find the Sibyl's bearings and distance. So I'm going to go from here to here, and it's this line right here that I'm actually interested in knowing the total distance of. So I'm going to say D. So now let's just resketch it, and I'm going to draw it a little bit bigger this time. I have something that looks like this. This is point A. We'll call this point B because this is where we changed directions. This is C where we ended up. I have a right angle here. I know that this here is 16 degrees. I'm looking to find this total distance here. And we know that this here is 2, and this here is also 2. So, to start out with, I'm actually going to have to use another right triangle, and I'm going to form that right triangle right here. So this is my right angle. I'm going to call this corner here D. I'm going to call this side length here lowercase c because it's opposite of angle C. And I'm going to call this side length here B because it's opposite of angle B. And before we move on, I know that this angle right in here, because this here is a 90-degree angle, 90 minus 16 is actually 74 degrees. So this angle is 74 right there. Now, if I can solve for side length B right here and side length C, I know that this side length here will be equal to C plus 2. So if I can take that side length, square it, add it to the square of B squared, I can then go and find D. So let's go ahead and get started. First, I want to find B. Well, B is related to this angle that I just found right here because it's opposite, and I know that this side length here is 2. So we can say that the sine, because it's opposite, of 74 degrees is equal to B divided by my hypotenuse of 2. So B then is equal to 2 times the sine of 74 degrees. And I did store this on my calculator, and I actually stored it as a letter B, but this gives me something about around 1.923. I'm going to do the same thing for side length C. Now C is actually going to be adjacent to, so I'm going to take the cosine of 74 degrees and say that that's equal to the adjacent side of C divided by the hypotenuse of 2. So then C is equal to 2 times the cosine of 74 degrees, which again I'm going to store, but this is going to give me something around 0.55. And from this information, I now know that side length, or this big side length right here, is going to be equal to C, which was 0.55 plus 2, or somewhere around 2.55. And again, I'm using the stored values on my calculator so I get a more precise answer other than 2.55. But by having this angle, or this side length here, and knowing what side length B is, I can then go and find this angle. So I'm going to take the tangent, because that's the opposite, and this is the adjacent side. So I have the tangent of angle A is going to equal 1.923 divided by 2.55-ish. Remember, if we do the inverse tangent, so the inverse tangent of this stuff here, and when I type that in my calculator, I end up with an angle measure of 37 degrees. So now, I want to convert that to a bearings answer. So to convert that to bearings, that's 37 degrees off the north-south line, and it's technically going in this direction, so I'm looking for this angle here. So I'm going to get to take 90 and subtract 37 from it, and we end up with 53 degrees. So my bearings then are going to be 53 3 degrees west of north. So this is the first part. Now I actually have to find the distance. So to find that distance, I know what side length B is, and I know what this big side length right here is. So if I want to find side length D, I can say D is equal to the square root of B, which was 1.923 squared, plus the other side length, which was 2.55 squared. And when you square those values, add them together, and take their square root, I get 3.19 nautical miles. And that then will conclude this example. So on that note, have a good night, and I'll see you in class.